Our next speaker is going to talk about IdleLeak, essentially how idle state in processors can leak information. He's Fabian Rauscher from Graz University. Take it away.
All right, thank you. So, how does this thing work? Is this a... Oh, that's the next one. Okay, I want to start this presentation with something with how this whole paper started. So, where can we find security issues in general? So a lot of people here probably are searching for security issues, try to fix them, and often you do something like a fuzzer, you have some static analysis, things like that. Or you look at the manual, and that is how this worked, how this went. I looked at the Intel manual and just checked out what's new in there. And here there are some new extensions that were recently introduced. One of them is this one here, user weight, tpos, umonitor, umweight. Recently introduced with the IdleLeak microarchitecture. I have an IdleLeak laptop, so perfect to test some stuff out. Okay, what does this instruction do, or these instructions? So one major thing those instructions do is right here. They put the processor into an optimization-dependent sleep state. And you have two different types of sleep states there. You have on one hand a lightweight power and performance optimized state, and also a more improved optimized sleep state. And those are the two. We have on one hand C0.1 and C0.2. C0.1 is a lighter sleep state with faster wake-up times, smaller power savings, and C0.2 here, slower wake-up times, larger power savings. And also this last part here, it improves the performance of other SMT threads on the same core. So typically when you have SMT, you have multiple logical cores per physical core, and they share some resources. Okay, so how much does this actually give us? Here we have some benchmarks. And what we did is we ran those benchmarks on one logical core. And on the sibling logical core, we either did busy wait or went into C0.2. So it's optimized sleep state where the other core gets faster. And for a few benchmarks, there was no difference, like IO U-ring and RD-rand. But for some benchmarks, there were significant performance improvements, like memcopy here. 100% faster, faster basically. And overall, there are a lot of performance improvements. So C0.2 is great. We should probably use that. Here again, some micro benchmarks with some instructions and how basically the same thing as before, how the instructions are affected by the other core being in this idle state. For some instructions like diff, there's no difference whatsoever. But other instructions, specifically nop, it gets almost 100 times faster to execute. That's great. So first thing, when we have something like that, we build a covert channel, and that's what we did. We did this covert channel first in a time-sliced approach, so you have a sender thread on one logical core, receiver thread, other logical core. The sender either does a busy wait or goes into C0.2. And the receiver thread just executes some NOP instructions because NOP gets faster if the other thread's in C0.2, so perfect for a covert channel like this. And if we want to send a 1, the sender busy waits. If we want to send a 0, the sender goes into C0.2. This is what this looks like for the sender. So if we have a 1, so those are like 512 NOP instructions executed by the receiver, because one NOP instruction is way too short. So if we send a 1, the NOP instructions take roughly 80 cycles to execute. If we send a 0, it goes down significantly to 60 cycles. There's also measurement code around that. That's why you don't see the full performance increase. So yeah. Also, there's those spikes here. That's when the sender decides which bit to send. So you can also somewhat see that in there. Okay. Now that's great. That's a covert channel, and also this thing is quite fast. We have native We ran this thing natively, and we had a speed of 7.1 megabits per second. We also did this through virtual machines, so across VM, significantly slower. But the main reason for that isn't because it can't be faster, but inside of the virtual machines, we can't really rely on a shared timestamp counter, so we used other things for synchronization, specifically synchronization at the beginning. We didn't optimize this too much, so that's why it's quite a bit slower. But it should come to almost the same speed if it's optimized enough. Okay, so that was nice. So performance increase, wonderful. What else is there with these instructions? So there's some wake-up reasons, so when this continues executing. And one thing here is it continues once a certain value is reached. You specify that in some registers. So you can say, please wait, I don't know, 1,000 cycles or something like that. And once the 1,000 cycles are up, continuous execution. That's very useful, I would say. And there are also other wake-up reasons. Other implementation-dependent events may cause the processor to exit the implementation-dependent sleep state. This is why I love to read manuals like this, because every time someone writes other implementation-defined events without specifying anything, then there's something there you can probably do. Also, interestingly, external interrupts also wake the instruction up. That's the same for similar instructions like, I don't know, halt, uwait. Yeah. Okay. Some examples. So this is normal. So we have one logical core that's sleeping in C0.2. And this logical core gets an external interrupt. And it wakes up. This is to be expected. That's what's written in the manual. Yeah. So now we're on the same page. Okay. Let's say the logical core is sleeping inside of a virtual machine, and we get an external interrupt. This also wakes up the thread. And you might say, while this is not documented, you might say, no, okay, this is kind of to be expected. For our instructions, it's documented what's supposed to happen. For this one, not, but yeah, let's continue with a different example. One logical core is sleeping. The other one receives an interrupt. This is specific for the lighter sleep state. This doesn't happen with C0.2. The thread wakes up. I'm not sure why, but it happens. Let's say the logical core is sleeping, and the other one triggers an exception. Those are typically, most of the time at least, internal to the core, so there's no external interrupts coming in. So it should be easy for the CPU to not wake up the other core prematurely. The core wakes up. That's odd. And of course, this also happens inside of virtual machines. Okay, so this is now wonderful. What are we going to do with this? First of all, of course, covert channel. So we have a sender and receiver, each on one logical core. One of the sender triggers exceptions or busy waits, and the receiver checks if any interrupt occurred through C0.1. Okay, we had speed here of 656 kilobits per second. It's not going to get any faster because at this point there is one interrupt or one exception per bit sent. So to make this faster, we would have to somehow speed up exception handling. Okay, so now we had a lot of covert channels, and covert channels are great to detect, to measure how much could be leaked with an attack. But let's talk about some actual attacks. So we did some fingerprinting attacks, and our basic setup was we have a virtual machine, and in this virtual machine, there's some malicious code running. Typically, when I have some code I don't trust, I put it into a virtual machine and run it there if I have to run it. And on some different logical core, there's you're browsing the web, or someone is browsing the web. And now if you access something on this browser, you get an interrupt, and if for some reason this virtual machine is on the physical core that receives the interrupts, you can detect them. Okay. First of all, so we took those detections, so those traces of interrupts, so when interrupts occurred. We put all of this into a short-term fast Fourier transform, and then into a neural network. The beautiful thing about the STFT is we have now this two-dimensional data which we can perform convolutions on and then do classification. This is not new. It's new for fingerprinting, but it's a technique used in signal processing. There are papers from, I don't know, 3 to 4 years back that already did this. But turns out this also works well with classification of those interrupt traces. Okay, first we did website fingerprinting. We took the top 100 websites from the Alexa top 1 million list. We had a closed world scenario. We once evaluated with the interrupts coming in on the core that the VM is running on, and also with the interrupts coming in on the sibling core, on the sibling logical core. It's not the same logical one, but the same physical core. And we also did this whole thing again with open world, so we have an extra class for all other websites, not in the top 100. And those are the results for the open world scenario. Confusion matrix with this beautiful diagonal down here, meaning most of the things got correctly classified. We got an F1 score here of 85.2% and 87.4% on the other class. For the closed world scenario, we were at around 93%. Great. So website fingerprinting, always a nice thing. A lot of people have done this before with some other interrupt detection methods. It's wonderful for comparison. But what else can we fingerprint? So what we did was we fingerprinted videos from streaming platforms. So we took 2 streaming platforms, platform number 1, very well-known platform, I think, and also platform number 2, a bit more privacy related. And we did the same thing there. So we took 20 videos that are popular on each of those platforms. We did the whole thing once closed world. We did it with the interrupts arriving on the sibling logical core of the VM. And also the whole thing again, open world. All right. This was my test setup back then, how I recorded the traces. This is actually in my flat, because I couldn't do this in the university, because for some reason the second platform is blocked. I had to explain this to my supervisor on why I need to do home office for a few days. It was an interesting conversation. But yeah, the results of this, video platform number 1. So we took the first 10 seconds of each video to classify it. If you take more than 10 seconds, of course, the classification will get significantly more accurate. For platform number 1, here, beautiful diagonal, we classified most of them correctly. We had an F1 score of 81.5%. Platform number 2, a bit worse, at an F1 score of 70.5%. Still a very visible diagonal. And the main reason for this significant difference is for platform number 2, the video quality is usually significantly lower of most of the videos, and there's also an intro at the beginning, and if you only record 10 seconds and use that for classification, it works a little bit less well, I would say. But if you take more, those numbers will most likely increase. Okay, to summarize a little bit what we did in our work. We analyzed security properties of C0.1 and C0.2, this new idle states introduced with these instructions. We built a high-speed covert channel. We did performed some website fingerprinting with high F1 scores. We performed a video fingerprinting attack, actually the first one that uses interrupts through a side channel, and also an inter-keystroke timing attack. We additionally discussed our results a little bit more detailed in the paper, and also discussed mitigations and things like that. And if you're interested in that, I invite you to read the rest of our paper. Thank you.
Let's thank our speaker. Questions?
Hello, great paper. Hassan from University of Waterloo. I just had a question. Do you see any, would this attack ever work across cores, physical cores?
This attack, as it is right now, does not work across physical cores in the sense that you can't detect interrupts on other cores. But if you, for example, browse the web on a website, on the browser, the interrupts for the network interrupts will usually arrive on some completely different core that is responsible for managing network interrupts or receiving them.
Okay, thank you.
Thanks for a great presentation. Nader Sabash, UCLA. So as far as I know, the C states and P states exist in the previous version of Intel processors as well. What has changed? Is it like it becomes available at the ISA level so you can actually kind of...
So the thing here is C0.1 and C0.2. Those are like substates of the running state, C0. Those are completely new.
Oh, okay.
And the important part for this whole thing is, I should have probably mentioned that at the beginning, those are unprivileged instructions that you can use to set the thread sleeping. So you can do this completely from user space.
But did you try to see if, like, for example, different P states or different other C states would result in similar things? Or?
We did not try this, but it depends. For speeding the other core up, I would assume so, yes. The wake up, so the detection of interrupts on the sibling logical core, no, that will most likely not work. I'm also quite surprised that this works because because you have two logical cores, but both logical cores have their own local APIC, so they will receive interrupts independently. So for some reason, the thread wakes up prematurely when there's some interrupt coming into the physical core.
All right, thank you so much.
Yeah.
Hi, thanks for the talk. I'm Nimish from Indian Institute of Technology, Kharagpur. And it would be interesting for us if you could share if you communicated this with Intel and what was their response about it.
Oh, yeah. We disclosed this to Intel. And there was no disclosure. I don't think they intend to do anything about it.
Oh,
That was.
So, the reason I was interested in this because, as you mentioned, these were unprivileged instructions.
Yes.
So from Intel's and in Tremont and IdleLeak and these like very newer generations. So
I didn't catch that. Can you please speak a bit louder?
In the newer generation processors, IdleLeak and the like.
Yeah.
So from Intel's perspective, we should expect that some user space application would be using them.
Yes.
For like idle states and management of the like. So if they are exposing unprivileged instructions to user space, which are exploitable, so one would expect that if we have a vulnerability there, then it should be fixed. But
yes, but I think where they are coming from, it's like, so those instructions are extremely useful, as we saw in the beginning. They give some huge performance benefits, and from their perspectives, the bad outweigh the good here. The good outweighs the bad here. So you have some huge improvements, and for major cloud providers, I would assume they just want them to disable the instruction if it causes problems.
oh, okay.
But yeah, for user space, the performance implications are great, so yeah. I don't know if they will ever do something about it in future hardware generations, but
Okay, thanks.
that's how it is right now.
I have a question also.
Yeah.
So those undefined behaviors that you showed on a specified behavior, are those consistent among different models, CPU models, and also are those consistent among like both Intel and AMD, or is this just an Intel problem?
So these instructions, or this extension is Intel specific. We tested, so this was introduced with IdleLeak. At the time, we only had IdleLeak and RaptorLake CPUs, so 12th and 13th gen, and it worked the same way for both. I would assume if the write unspecified, it might change depending on newer architecture, so it might change in the future. Maybe it just doesn't work anymore in, 5 years. I don't know how long it takes for them to completely build a new architecture, but yeah. it might change.
Thank you. Let's thank our speaker one more time.